I think the audio is probably right. So.
Yes, that's right.
Okay, our next speaker is Professor Bielak, who I think will use the computer and the slides.
Ladies and gentlemen, I would like to present some results concerning chromatic polynomials for some recursively defined families of graphs. I recall the definition of the chromatic polynomial, denoted here by P of n. What's happened? Okay, sorry. The chromatic polynomial is denoted here by P of G in G and lambda. G is a graph, and lambda is a variable. And if lambda is integer positive number, that we count in this way the number of proper coloring, vertex coloring of the graph G using lambda colors. Yes. I would like to tell something about the zeros, the location of zeros of chromatic polynomials. The problem is related to some phenomena in statistical mechanics, as we heard from the lectures presented by Sokal, Schrock and others. I here would like to present some special family of graphs, so-called medial graphs, because they play some special role in study Petri works. In computing of the chromatic polynomial, we as all use the famous reduction formulas discovered by by Whitney. This is the formula, and the gluing formula presented here. This formula are very nice, and I use this for counting the explicit form of the chromatic polynomial for some families. And first, I would like present the definition of medial graph, because I would like consider this special case of family. What is the medial graph? The medial graph is defined for a planar embedding of a graph. Say, let our planar graph be denoted here by black color, this black vertices and this black edge. And the medial graph is constructed from this embedding of the planar graph as follows. For each edge of the basic graph, considered as a planar embedding, we put red vertex of the medial graph. So the vertex set of the medial graph of a given graph G is exactly the edge set of the graph, of the basic graph. Then we consider edges between red vertices. We put red edge, the red edge is edge of the medial graph, as follows. Edge red means that the vertices, this red and this red vertex, are adjacent in the medial graph because they are on the boundary of the same region, and they have common end vertex. If some case the vertex and this vertex are two common vertices, then we can consider this edge and this edge, because we consider one edge per each vertex rotation per each rotation concerning common vertex of these black edges. So we have in this case, if we consider such medial graphs, we obtain 4 regular planar graphs. These graphs can have parallel edges or loops. But if we would like to count chromatic polynomials, we know that we can delete loops and parallelism. So in fact, we consider maximal spanning subgraph of the medial graph, and I call this graph a quasi-medial graph and denote it by capital M of G. Yes, for these cases we have these respective quasi-medial graphs. So, this is formal definition. What I presented before a moment. Yes. Yes. So we now interested in chromatic polynomial of quasi-medial graph, and I would like to present a family of Hamiltonian medial graphs of sufficiently large order with chromatic complex 0 in some disk where D is defined as the average degree of a graph. This idea to set in such middle of the disk, I think that it is idea of Professor Biggs. The radius of the disk can be counted as follows. It should be greater than some number A with index 0. This number can be counted as maximum positive root of some polynomial equation.
With chromatic zeros in the disk, do you mean all of them are in the disk, some of them are in the disk?
It is some disk because I have some families of medial graphs.
No, but I mean for
Yes.
the given graphs. Are
For
you
the given
saying
graph.
that all of the chromatic roots lie in this disk?
In this disk,
Okay.
yes. I can count this radius of the disk. Yes. So we can remember the definition of medial graph, and now would like present some family of such graphs. Yes. In fact, I have here 3 kinds of graphs: G sub n, F sub n, and H sub n. The first graph on the top of this figure is a medial graph. As you see, the medial graph of the Cartesian project of the paths of order n+1 and the complete graph of order 2. Yes. We can check this maybe easily. This is quasi-medial because we delete this parallelism of some edges. And this second graph can be obtained from the first by, we know, we can extract the edge 0, 1. Then we can also observe the relation between the last graph F sub n to the graph G sub n. We can consider G sub n as graph obtained from H sub n by extracting the edge 0, 0 prime, or by extending the vertex 0 in graph Gn, we can obtain this graph H sub n equivalently. Now we denote by capital letters G sub n in lambda, G f sub n, and H sub n in lambda, the respective chromatic polynomials for these graphs, G sub n, f sub n, and H sub n, respectively. We would like to count mainly the chromatic polynomial of this quasi-medial graph G sub n. How we can do this? We can do this, as I said before, by applying witness reduction formula and gluing formula for this graph. Oh, sorry, not the moment. And we have some special small cases. We can count simply these chromatic polynomials in the case where we have index n. And then applying the witness formula, we get the following relations here. And here we have the graph f sub n. But we count also the chromatic polynomial for this graph using the G sub n minus 1 and H sub n minus 1. And respectively, H sub n is in this chromatic polynomial are involved these two chromatic polynomials. So in fact, we have some possibility to get matrix equation of the following form, where these three chromatic polynomials are related to the chromatic polynomials for the graphs with indexes with subscripts n minus 1, with A, where A is a transfer matrix of the following form. So in fact, we have some linear recurrence relation in this moment, and we can count the result. So we have here a relation to the chromatic polynomials presented some pages before for some simple cases. But this is true for n greater than or equal to 2. By theory of such recurrence equations, we have the following explicit formula for chromatic polynomials of each of these graphs. Here, lambda sub n, lambda sub 2 are non-zero eigenvalues of this transfer matrix A, and G sub 1, G sub 2, and similarly H with subscript and F with subscript are some coefficients in variable lambda. So if we would like discover the explicit formula, we should count these coefficients and these eigenvalues. These eigenvalues, these non-zero eigenvalues, are in fact the non-zero eigenvalues of the submatrix of this previous matrix B, presented here, and they are of the following form. Yes, here we have some parameter defined here. Yes. These eigenvalues are different outside the following sets, but here I have mistake. We delete this. Delete this. Yes, I return. You show here we have the roots of this following polynomial only. Yes. So we can count the chromatic the chromatic coefficients. Can we say? From the following equations, sets of system of equations, and so we get this as follows. Recall that U is here, and this symbol denotes the following polynomial. And the same we can do for coefficients f sub 1 and f sub 2. So if we consider this fact by the previous the previous equation for the chromatic polynomial of these three graphs, we can note that these chromatic polynomials are given in terms of some analytic functions, so we can study the location of the zeros using the special method from this branch. Yes. Now I would like to present another family of graphs. Medial, quasi-medial, it will be better. Yes. Yes, we have here some family denoted by L sub n comma p here, and some another family B sub n comma p. The first graph L sub n comma p is constructed from the cycle of order n by replacing each edge of this cycle by some theta graph, namely theta graph having two edges, two paths with two edges and one path with p minus 1 edges. So we also have to consider this simple case for counting the respective chromatic polynomial. This graph is really obtained by the medial construction from some special graphs. Namely, we can build some cycle of order 2n. If you consider the graph L sub np, we take the graph of the cycle of order 2n, and we replace each edge belonging to a perfect matching in this cycle by p edges in parallel. So, for example, here we have p edges in parallel. And for such a graph, it is planar embedding, some planar embedding, and for such graph we build medial graph. So we, as according to the construction, we put, we set vertices here, this new graph, and here and here. These parallels we really delete. So in this way we can obtain a graph of this shape. So if we now denote by small n p in lambda the chromatic polynomial of the graph L n p, and by b n p in lambda the chromatic polynomial of the second graph is obtained from the longer cycle than c sub n. We obtain this from c sub n plus 1 by replacing all edges instead of one in the similar way as in the previous case. Then we have the possibility to obtain the following formula for chromatic polynomial of the graph of the first graph. We are interested in this chromatic polynomial. Here we have a function f being simply chromatic polynomial of this theta graph over lambda. This theta graph which replace each edge of this cycle. It's the same tetragraph. It is really this tetragraph polynomial, chromatic polynomial. And the second function, g sub p lambda, can be considered as some combination of chromatic polynomials of these two cycles over lambda lambda minus 1. Yes. If we set some notation, and here is sp lambda, this function, hp lambda is this function. B sub 1p is chromatic polynomial of these small cases for this kind of graph. B sub, oh, here. Okay. How to obtain this kind of result? Simply by reduction formula of witness and gluing formula. Yes. Namely, we can apply the Whitney formula for the non-edge with ends u and v red points in this figure in the graph L sub np, and we obtain these two graphs into parallel lines, and we do with the second graph B sub np for non-edge u w, and we obtain the following two graphs. So we can observe some special gluings here, and so we really get the following result. So we can express LNP and BNP in this way. A is the transfer matrix denoted here. S and H are functions presented before. So we can account further, and we have the following result. Simply, we are now interested only the first kind of graph. We have here a simple recurrence relation, but if we set something else for simplicity, the parameter a and t, we can obtain the following recurrence relation. And we now can use the method of generating function to solve this recurrence relation. If we consider rational generating functions, we can find that for this case we have such rational generating function. Yes. So the chromatic polynomial LNP in lambda is simply some special coefficient in the formal power series of this generating function. So we can express this as follows, and finally counting something and considering something special cases, we have really this formula for integer positive lambda. For some special cases, lambda real or complex, we have critical points sometimes. But in fact, we prove the following general formula, yes, as proposition set. So we can now look for the zeros of this chromatic polynomial. If you consider a complex plane, then instead of our lambda, we can, where is it? We can consider z, variable z, complex number z. Then I would like to present some result for p in lambda and p in z for p equal 4, 3, or 2, for sufficiently large n. We can express in general fp, the function fp, and this function in the following way, or equivalently in this way. We also can express the function g p in p and lambda as follows, and we consider some disk. Here is the average degree over 2, and we are interested in the following inequality. For the case p equal 4, we have in this fact the following theorem, that this R, the radius, is of the following form. This radius is greater than R0, where R0 minus 2 over 5 is maximum positive root of the equation, of the following equation. Yes. To prove this, we use really the method of presented by Biggs to find this center of the disk, central point, and we also use the famous Roche's theorem discovered for monomorphic functions. This theorem. So we can count how many zeros are inside of Jordan cover. For some special cases, if we consider polynomial, we can really use this theorem. So for this case where we consider p equal 4, we can have such explicit formulas for f and g, and we can count lower bound for the moduli of this function and the upper bound for the moduli of these functions. So if you would like to this inequality be true, it is enough to consider the following. If this second inequality holds, the moduli of the first function is greater than or equal to this second one. We really, in this fact, can solve this inequality, but by finding the maximum positive root of the following one. So if we set R0 in the following way, we can count it approximately to this number. So we observe that all zeros of the function f for and z lie in the following disk. So all zeros of the function lies also in this disk, where R is greater than R0. So by Roche's theorem, we can conclude that all zeros of this chromatic polynomial lie also in this disk. Yes, for sufficiently large n and R greater than R0. Similarly, yes, I finished. I present only this fact and this one. Maybe I would like to remarks. Some other information we can get from Gauss-Lucas theorem, from this small proposition, and other information if we would like to read something, you can find at web seminar pages. Thank you for the attention.
the accumulation set of the zero?
I have some page. I have some page. But I suppose that if I have more knowledge from learning in this seminar, I can do something else. Yes. Yes. Thank you very much.
You mentioned that your graphs are medial or quasi-medial,
Yes.
and I guess your first family are Hamiltonian.
Yes.
But you didn't seem to use those properties anywhere. Is there some?
Exactly.
Do you think they play some role?
I only starting for to study this problem. Maybe I consider some other properties. Yes.
So we thank our speaker.
Thank you.